Hey everyone, Mr. Fritz here, and wait a second, that's not right. Perfect. In this video, we're going to talk about graphing the cosine function. We've graphed the sine function before, now we're going to talk about graphing the cosine function. And really, it's not all that difficult. It's very similar to the sine function. We'll see some of the similarities and some of the differences. So what we're going to do is kind of like what we did with the sine graph. We're going to start with the unit circle and try and get our values for the cosine curve. One thing that's a little bit tricky is you remember on the unit circle, the cosine is the x value, but when we are graphing y equals cosine of x, we're really saying that like the x is like our theta in the graph that we make. So the xy values of the unit circle, not the same as xy values of my graph of the function y equals cosine of x. So just want to clear that up. If we go back to our unit circle and we think about what all of these special values are around my quadrants, when I go around, I'm looking at the x values to establish my cosine of theta. And if I take a look at the cosine of negative 2 pi, that's a full rotation around clockwise, and the x value there is positive 1. And if I go around a negative 3 pi over 2, that's going to go all the way up to here. The x value here is 0. If I were to now go a negative pi radians, I'm at negative 1. If I were to rotate a negative pi over 2, that's back to 0. And then I'll fill this in with 0, pi over 2. We're going to continue to go by increments of pi over 2. Pi, 3 pi over 2, and then 2 pi. And the pattern will continue. At 0, the x value is 1. So the the cosine of 0 is 1. The cosine of pi over 2 is the positive direction, that's 0. The cosine of pi is the x value here, that's negative 1. And then I continue 0 and then back up to 1. So now we're going to plot this onto the grid. And again, now I'm trying to graph y equals cosine of x. So the x is really, you think of like theta as x, and the y values are with the outputs when I put in these different rating measures in the cosine function. So I know we're seeing like lots of different uses for y's and x's and thetas and things like that, but hopefully we can start to translate this table into this graph. So the first thing I'll do is I will make a nice graph. I'll go up every 2 boxes. Let's say we'll go 1, and we'll go down 1, and then let's go every 2 boxes is pi over 2. Okay, great. Now we have the grid set up. Let's start to plot these values. Let's do this in another color. So at negative 2 pi, I have a y value of 1. When x or theta is negative 3 pi over 2, the y value is 0. And then I'm actually going to just continue my typical sinusoidal pattern of going up and then down through the midline to the min, back up to the midline, and then up to the max. And we'll connect this, making a nice smooth curve, something like this. You might be thinking, hey, that looks a lot like a sine graph. And guess what? You're right. It looks a lot like a sine graph, just kind of shifted over a little bit. So, and let's talk about why that is. But first, here's how I remember my general graphing pattern. This is just the typical y equals cosine of x. And I like to think of them, I mean, we're going to be stretching them, we're going to be shifting them, but as long as we remember this pattern, we'll be able to generate different cosine functions. When I think about my key x values, just like I did in my sine curve, that's going to be every quarter of my period. So in this case, the typical period is 2 pi, just like before. And so my key x intervals or values are spaced out by pi over 2. So my first key value is starting at my max. And my next key value is going down to the midline. Then my next key value is going down to the minimum. Then back up to the midline, and then finally up to end at the max. So really the big difference, the pattern is exactly the same of this up and down undulation, just like the sine curve. The thing to remember is that the cosine function begins at the maximum, not at the midline. And if we've got that down, then we shouldn't have too much trouble graphing cosine functions. So let's just quickly compare the two. So we've talked about the similarities in shape, and I want to just look at the two of them together. So why don't you sketch the sine curve and the cosine curve right on top of each other. So this right here is y equals cosine of x in the red, and in the blue is my sine function, y equals sine of x. Look very, very similar. They are actually just like phase shifts of one another. And in case you didn't know this, the reason why we call this the sine and the cosine function is if you actually notice the difference between these two, graphs. Let's just take this minimum and this minimum, and let's figure out just how far apart they are. That's a distance of pi over 2. Now if we think in our degree brain for a second, pi over 2 radians equals 90 degrees. We've got a specific word when things add up to 90 degrees. Those are complementary angles. They are complementary angles. The sine and the cosine are related and just shifted 90 degrees away from one another, or pi over 2 radians, because they're complementary functions to one another. So they really look exactly the same. Anything that you could graph as a sine, you could also graph as a cosine. Exactly the same, just shifted by exactly pi over 2 radians. So, big idea here. In the next video, we'll actually talk about graphing some of these examples, and we'll see how we can use the transformations in the cosine function.